Hello everyone, my name is Hadi Bekmambari. I'm a PhD student at Bosch Center for Artificial Intelligence, and today I'm going to present our paper learning Riemannian manifolds for geodesic motion skills. We use learning from demonstration to be able to reproduce robot motion as simple as grasping or harder tasks like opening doors or walking. So there are several methods based on dynamical systems, neural networks, and probabilistic methods that can provide a platform to learn these skills. Regardless of the approach, the learning methods should be able to deal with full post-trajectory learning, changes in the environment like obstacle avoidance, and multiple solution trajectories. We combine all these features and introduce geodesic motion skills. In other words, we build Riemannian manifolds, which are smooth differentiable surfaces whose underlying structure is defined by Riemannian metric by encoding the uncertainties in the demonstration data using tools like variational autoencoder. Given the metric, we can find underlying patterns in the data using geodesics, the locally shortest path on the manifold, which later can be used as robot motion. But why Riemannian geometry? So the main reasons are they are very powerful tools for modeling the nonlinearity of the data. They have a high capacity to learn and reconstruct the relevant patterns in the robot motion data, and finally the flexibility of the formulation gives freedom for considering changes in the environment like obstacle avoidance on the fly. But of course, there are problems like recursive dimensionality, and to deal with this problem, we have to make some assumptions. First, the data is sparsely distributed in the ambient space. The data lies on a manifold in a lower dimensional latent space, and this manifold is actually a Riemannian manifold. So we explain the method in three different steps: learning Riemannian manifold, computing geodesics, and generating motion. Each in three different experiments: a toy example, a real robot grasping scenario, and simulated robot pouring scenario. In the toy example, the data is defined in R2 and S2, which is a simpler version of position and quaternion data in robotics. Data in S2 looks like a character C in an antipodal manner, and the data in R2 looks like character J on a 2D surface. As we mentioned, we use a variational autoencoder for extracting the uncertainty. The VAE learns to reconstruct the data as close as possible, meanwhile providing a regularized latent space. So in this case, the decoder has two parts, one for R2 and the other one for S2. The R2 decoder is pretty straightforward and looks like a traditional decoder, but for S2 the decoder has to respect unit vector size and antipodality of the data. To do so, we force the decoder output to be a VMF distribution instead of a Gaussian. So by nature, the unit vector size is respected, and to consider the antipodality, we use a mixture of VMF distribution, in which one of the mean vector points at the opposite side of the sphere. To capture the geometry using uncertainties, we define the Riemannian metric, so-called pullback metric, using the decoder network. Here you can see our metric is combined of four words. Each term corresponds to either mean or variance in R2 or S2. For example, the first term corresponds to the metric regarding the mean in R2, where J represents the Jacobian of the corresponding decoder mean or variance network. The visualization of the resulting metric shows a boundary around the latent codes, which are also called high energy regions. Geodesics to find the shortest paths tend to stay in low energy regions. This animation shows a barrier that is enforced by the metric around the latent codes. To compute geodesic connecting 2 points on the manifold, this barrier will guide the geodesic to follow the trend of the data by following the low energy regions. By decoding geodesics, we achieve a motion trajectory similar to the demonstrations. But regarding obstacle avoidance, since the obstacles are not defined in a latent space, we have used an ambient space metric. The simple example shows the obstacle is defined as a normal distribution. This means the points that are in the ambient space that are closer to the obstacle will get a high value. Therefore, by multiplying this metric to the metric we already have, we get a new metric that has high energy regions around the obstacle. This short animation shows that there is an obstacle that has a high energy region around it, which repulses the geodesics. Here you can see some example on real robot dataset. All this geodesic on the top right side will produce the same motion. On the right side you can see a simulated robot following a decoded geodesic in the ambient space. And here you can see more examples like reorientation and grasping from top with and without orientation. And here we show you a multiple solution trajectory created from the synergy of all demonstration. As you can see, the geodesic has used three different set of demonstration to come up with a completely new trajectory that was not demonstrated to the robot beforehand. And finally, in this video, you can see the robot is able to do the pouring task and avoid the obstacles at the same time. Thank you for your attention. I will be happy to answer your questions now.